Hey everyone, welcome back. It's Typhoon here, and today we are diving into some really exciting stuff. But before we get into that, let's quickly recap what we did in the previous lecture. In the last lecture, we have working with the vulnserver application, trying to hunt down a buffer overflow vulnerability in the run command. So, we started by sending different amounts of data. The first 50 characters to the run command, then 500, and then 5000. So when we sent 5000, the program has crashed. And we noticed that something really interesting. The EIP register was filled with 41414141. So if you remember, that's just a text representation of the letter A in ASCII. So this was our first big clue that we had a buffer overflow on our hands. Now, to figure out exactly where our 5000 characters the overflow happened, we used Metasploit's pattern create.rb tool to generate a unique pattern. So we sent this pattern to the server, and surprise, it crashed again. So we checked the EIP register, and sure enough, it was overwritten with a specific somewhere here 4-byte value from our pattern. Now, to pinpoint exactly where the overflow occurred, let me find that. So to pinpoint exactly where the overflow occurred, we took that 4-byte value and plugged it into pattern offset RB, and this told us that the overflow happened after after 2006 characters. So 2006 characters A is filled with the buffer, and then next 4 bytes overwrote the EIP here. So finally, to make sure we were right, we crafted a script. Let me find. So finally, to make sure that we were right, we crafted a script that sent 2006 A characters, 4 B characters, and rest with C characters. So when we run the script, and boom, the EIP register here, as you can see here, filled with 424242, just like we predicted, which is B in our ASCII. So this confirmed that we had a full control over the buffer and could overwrite the EIP. So that's where we left off. And in this lecture, we are going to take the things to a step further. We will start injecting shellcode into that buffer and really see what we can make this server do. So in the previous lecture, we gained control over the instruction pointer, which is a huge milestone. Now our goal is to inject shellcode and redirect the instruction pointer to execute it. Now, to make this work, we need to find a suitable place in our memory for shellcode. The best place to do that is the stack. So now we will go back to our Windows machine. We'll go back to our Windows machine right here. And we'll open the immunity debugger, as always, administrator. Yes. Here. Now we will also open the vulnserver. Click on File. So we will need to attach this vulnserver to immunity debugger. Oops. Yeah. We had 2 immunity debuggers open. Actually, first close that, close all of them. Okay, open a new one, run as administrator, file, attach, and vulnserver. And here we are. We need to search for instructions now. Now we will go there, right click on this tab. Here we will go to somewhere search for and all commands in modules. So this allows us to search for any instruction, whether it's in a vulnserver itself or in any related libraries. And here we are searching for GMP ESP here. So we are looking for the GMP ESP instruction here, so which will let us jump to the stack, and in search bar, as you can see, it is come here pre-written, and we will click on find. Okay, search again, and all commands in all modules, and find here. That's it. So here, when you find this GMP jump ESP instruction, note down the address. So let's say we find it in kernel 32. It should be somewhere here. Let's actually. So as you can see here, we have that in RPCRT, like kernel base, mswsoc here, and we also have ess function.dll. So also I want to talk about something about ASLR. So this is a quick tip. So you can use any library, not just like kernel or this specific library or this specific library. However, keep in mind that if you use system libraries like rpcrt4.dll, ntdll.dll, kernel-base.dll, and also mswsoc.dll, these addresses change each time. Each time Windows boots up, due to a security feature called address space layout randomization, it just changes. And we will dive deeper into ASLR in later lectures, but for now, just remember that if you choose a library specific to the application, not the system, the address is more likely to remain consistent. So in this case, we will select the last one. With my experiences, the last addresses is less changing, or it won't change anyway, because it is the application library, right? So we will select this last GMP ESP here address, this one. And now we will edit our exploit script. So that's it with our application. We can close the Immunity Debugger now and go back to Linux. Here we are. I copied this here. Now we need to generate a shellcode, right, for accessing to the vulnerable machine. So what we do is we will use msfvenom. So we need to generate a shellcode that will be injected into vulnserver. So we will use this tool msfvenom. Now msfvenom. I will write this code and explain later. Let's also get rid of the bad characters. And it was, yeah, 0D. That's it. lhost is gonna be this. And lport, let's say 4321, and f python, because we are using Python. Now, msfvenom. Let's start with msfvenom here. So this is a versatile payload generator provided by the Metasploit framework. It allows you to create various types of payloads, including shellcodes in different formats. So why use it? It's incredibly powerful and customizable, making it ideal for creating a payloads for different architectures and platforms, just like what we are doing here. This x86 here, this A flag specifies the architecture of the target machine. In this case, x86 indicates that the target is running 32-bit architecture. In this case, we are running the 64-bit, but the 32-bit will do just right. So this shellcode needs to match the architecture of the system, of course. So since vulnserver is running on 32-bit version of Windows, and vulnserver is actually 32-bit, we specify x86 to ensure compatibility. So if your system runs 32-bit as well, and you try to generate a 64-bit payload, the payload will fail. And here we also have the platform Windows option. Of course, for this one, oops, I made a mistake. We need 2 here. So this platform flag tells msfvenom which operating system the payload will run on. Here we are specifying Windows, since vulnserver is running on Windows machine. So why is this important? This ensures that the shellcode is generated specifically for Windows, or using Windows compatible system calls and conventions. And here this is our payload. So this P flag specifies the payload to generate. In this case, Windows shell reverse TCP. This is a payload that creates a reverse TCP shell. So this is a reverse shell is where the target machine, this vulnserver in this case, connects back to the attacker's machine, giving the attacker a remote shell. So this is particularly useful in bypassing firewalls that might block incoming connections. And here we are, this P flag. This P flag allows us to specify bad characters and use that should be avoided in the shellcode. Sometimes, always, almost always. So in this example, 00, 0A, and 0D represent the null byte. The 00 represents null byte, 0A represents new line, and 0D represents carriage return. So why exclude these characters? So these characters can cause the shellcode to break or terminate early. And for instance, 00, null byte, is often used to indicate the end of the string in C. So including it would truncate our payload. So here we have lhost. This is lhost stands for localhost, which is the IP address of the attacker's machine. In this case, our Kali Linux machine. So this is the address that vulnserver will connect back to when the reverse shell is executed. So you need to specify the correct IP address here to ensure that the reverse shell connects back to you. And we also have the lport here. Lport stands for local port. This is the port on your machine that will be listening for the incoming connection from server. So why this port? So you can choose any available port. In this example, we are using port 4321, and make sure your machine's firewall isn't blocking this port or connection will fail. And here we also have Python with F flag. Here we are. So this f flag specifies the format in which the shellcode should be generated. Here we are asking for Python code. And why Python? Since we are writing our exploit script in Python, generating the shellcode in Python format makes it easy to directly integrate, like copy and paste into our script. So what's next? So once we run this command, we will get a Python snippet with the shellcode. Let's check if everything is correct. Yes. Now this is the Python snippet of this shellcode that we can inject into vulnserver. This shellcode will give us a reverse shell, allowing us to execute commands on the target machine. Now that we have our shellcode ready, let's walk through the final exploit code line by line. So this script will send our crafted payload to the vulnserver and, if successful, give us a reverse shell back to our attacking machine. Now we'll copy that, open, and now we will click a new Python file, and now we will name it exploit.py. Now we will firstly import the socket. As always, I will explain this code line by line after writing it. Server IP. Let's see if this IP is true. Yes. And remember what was our code here? Let's also comment that here. My socket. Socket.socket. Socket.af inet and socket.docstream and my socket.connect the server IP and port. Now we will also need to get this print. So we will need to print the like output that we will get from our vulnserver. Okay. So print my socket to receive and now we will need to generate our junk. As you remember, we will need to just enter some characters, 2006 characters, bytes, 2006 bytes, and now we'll also need to define the EIP register. In this case, as you can see here, this is 62501205. So we will need to write this reverse, like 051250 and 62, like this. So x here, x05 1250 and 62. Now we will paste our buffer here. Here we are. And now we will create a new variable named injection. We will add EIP. Ops, and we also need to develop the knobs to sure. So Ops is gonna be like after, let's see, yeah, let's define it after junk. Ops is gonna be like 64 64 9 zeros. And yeah, we are injecting junk firstly 2006 A characters EIP. This is the EIP register and knobs. And after that, we will also, or we do anything for the buffer here. Now, off. So my socket that send the run here plus injection plus rn, and again print my socket receive 24 and my socket dot send exit rn dot encode here, and finally we will close the my socket dot close. So now I will explain this line by line. Firstly, at here we are importing the socket. So this line imports Python's socket library, which allows us to create and manage network connections, and we need this to connect to vulnserver running on the target machine. And we also have the server IP. So this variable stores the IP address of the target machine running vulnserver, and here replace this IP with the actual IP address of your target. And we have the port. This specifies the port number on which the vulnserver is listening. Default port for vulnserver is 9999, and this is just a comment. This probably indicating the memory address that we found that in EIP. So we will use here just to remind us. So, but you can also add like more comments on your Python, so to keep documenting everything. So here also we have the my socket. This line creates a new socket object af enet and sock stream. So this line creates a new socket object. This af enet specifies that we are using IP version 4, and sock stream specifies that this is a TCP socket. And now we also have the my socket connect, the server IP and port. This command connects our socket to the target machine at the specified IP address and port. And once connected, we can start sending and receiving data. Now we are printing my socket here. After that, with which receives and prints the initial response from one server after connecting. So this helps confirm that the connection is established and that server is responding. And junk here, so this creates a string of 2006 A's, which will fill up the buffer right up to the point where the EIP register is overwritten. So this was determined from our previous pattern offset calculation. And we also have the EIP. This line defines the address that will overwrite the EIP register. Here 05125062 is the address of the jump ESP instruction in like we found that in Let me see the DLL name. Just forgot. Server, server. Yeah, we found that in here, which was for the connection DLL. Yeah, ESS function.dll. So this address points to the this is the address of the GMP ESP instruction in ESS function.dll. So this will redirect execution flow to our shellcode. And here we have knobs. This is the new one you saw in our course. So knobs, this create a no operation sled. The 90 is the opcode for a knob instruction, and 64 of them give the CPU some padding to safely land on before executing the shellcode. So this increases the reliability of the exploit. And we have the buffers that we created with msfvenom. It's a series of bytes that, when executed, will give us a reverse shell back to our attacking machine. And here we have the injection junk EIP knobs buff. This combines the buffer overflow payload. First, we have the junk 2006 A characters followed by the EIP address of GMP ESP. Then the knobs, knob sled, and finally our buffer overflow in the shellcode. Now, also we have the MySocket send, as you saw this line in previous lectures. This sends the crafted payload to the vulnserver via the tran command. So this is the moment of truth where we attempt to exploit the buffer overflow and execute our shellcode. Now we also have print. This receives and prints any response from vulnserver after sending the payload. This is useful for debugging and verifying if the exploit worked. Now we also lastly have the send. This sends exit command to the vulnserver to close the connection gracefully, and the encode function converts the strings to bytes, which is the required format for sending data over the network. But if you want to like analyze this vulnserver program and find more vulnerability in this, you can also just delete this line and just don't use it at all. And after all, we are closing the socket connection, and this is important to release the resources and end connection cleanly. And that's it. This code, when executed, should trigger a buffer overflow in vulnserver, overwrite the EIP register, and execute our shellcode, ultimately giving us a reverse shell. And now we will try that. We will also, let's open the windows here. Go to back CMD and see here LVP 4321. We are now listening any connection that has the port that 4321. We'll also open the vulnserver, and on the other here we will do the shellcode python .py, and as you can see here, Congrats everyone, we have successfully executed our exploit, shellcode, and despite Windows Defender raising an alarm, it still ran in memory. So this shows how some exploits can bypass defenses and execute as intended. And in next session, we will dive deeper into refining these techniques and evading detection. Great job today, keep pushing forward, and as always, happy hacking.